Okay, so welcome to this open lecture. We call it Meeting the Experts. So today we have Matthew Tam. He's product manager at Caramba 3D. It's one of the best FEM modelers inside a Grasshopper environment. And for the whole community and for us, it has been a game changer because we have been able to design and analyze the structures. And it has been very important to have this feedback loop. And the relationship between the form and its performance can be very evident. So we are very happy that he is joining the master, and he will be joining us doing a workshop, these 2 days, just reviewing your projects and assessing you in how to translate your ideas into a structural model. Okay, there's always like a translation to make. There's like you're making an abstraction. I like to think, and I always tell students that it is really, really important to be able to. I mean, we can only build what we are able to draw and calculate. Okay, it's. I mean, before there was a big there was a very big leap, between what we could draw and what we could draw by hand and what we could draw digitally. But now it's becoming easier. But it's really important to be able to have this confidence in the geometry you are building, and make sure you are properly calculating it. So, well, without further ado, thank you for coming, Matthew, and all yours.
Thank you, Ricky. Okay. Do I have to switch it over? Oh. Okay. So I'm going to talk a little bit about Caramba 3D. I think you've all been using it in your course already a bit. You had some tutorials from Mark, one of our colleagues in Frankfurt. And I'm also going to be showing you some of the use cases where Caramba has been used in some of the projects at Bollinger+Grohmann. Just a bit background about our office. We are a group of engineers originally based in Frankfurt, but now we're situated in over 19 locations all around. Is it blurry? Was it? Is it okay? So I'm based in Vienna. I think it's better now. Oh. I'm based in Vienna, where we have a big sort of computational design team. Is it better, or is it no? Is it better? Yeah. Yeah, it's better. I think maybe it's better now. Okay. So I'm based in Vienna, where Caramba was first initiated as a sort of research project, and I'll be talking a bit more about that later on. Some of our key milestone projects, if you are not aware of Bollinger+Grohmann, the Rolex Learning Center in Lausanne by Sana Architects, is 3 forms of concrete shell structure, a very beautiful space where students can sort of. Do you still hear the echo as well? Is it better if you use that, or? Maybe. I'm not sure. Is it better like this?
Yes.
Yeah. So these are some of the key projects. The Kunsthaus Graz, for example, by Peter Cook, one of the very early projects where we used even Rhino, one of the first Rhino versions, I think even a better version of Rhino. And the European Central Bank by computational was where the first, let's say, stages of Caramba came into play, where we were trying to optimize the position or the bracing elements of the double towers or twin towers. So workflows are a very important sort of aspect of how we work at Bollinger+Grohmann, and how Caramba also came out sort of through the development. So this came from the sort of collaboration with many, a wide array of architects who work with, let's say, complex geometries. So the UFA Cinema by computational, one of the very first sort of deconstructivist projects, where we had to really understand how to realize and construct these types of complex structures, right? So using the very first iterations of FE software. So RFM is a software that we typically use at Bollinger+Grohmann, widely used across Europe for calculation. Crumba itself is an FE, finite element modeling software, where you can do calculation of structures. And this is where we first used the computer to, let's say, calculate structures. The Kunsthaus, as I already mentioned, where because of its freeform geometry, the complex shapes, the sort of organic nature of the project, one of the first iterations of Rhino were implemented to really do the NURBS modeling. So we worked very closely with the team at Peter Cook and Colin Fournier to be able to realize this project. And optimization, which you've probably heard of over the last years, it's not so, let's say, a hot topic anymore, but back in the day, optimization in the sense of how can we, let's say, take a project that's what we say is maybe more conventional and use, for example, genetic algorithms or the computer to help us find better or different types of solutions. So optimization in this stage is where we come up with, let's say, a design space where we have different parameters that we can play with, and we let the computer, let's say, go through many different iterations. These iterations are evaluated, assessed for example, different objectives, and then we pick the best ones, and we do this over many different iterations until we find, let's say, the best solutions. And then we get always, let's say, a pool of optimal solutions which we can pick that are based on different objectives. So together with, let's say, the architects or designers, you can go through and pick and choose specific structural solutions that might fit best to that architectural design intent. And so this has led to, let's say, what we call now the Design Technology Group at Bollinger+Grohmann, where we deal with a lot of these topics relating into computational design. So now we're dealing more and more with data. So how does data play into the role of our everyday work? So it's not just the model itself, but you probably all have heard of BIM. BIM, let's say, often associated with just Revit, but there's much more than BIM than Revit is. So how can you use this data to leverage your project and project workflows? Optimization, as I already touched on. Connectivity or interoperability. So now we work with many different tools in many different environments, and often the challenge is how do you translate this geometry or this information from one platform to another platform. And often different software environments don't want to talk to each other. So one of the big challenges is how do you then translate this geometry, let's say that comes from an architect in Rhino, to a structural model in RFM or Crumba, for example, into a BIM model, for example, in Revit or ArchiCAD. Workflows, as I mentioned, where we try to assess the implication of our structures on, let's say, existing structures too, or let's say the environment. Analysis and simulation, of course, is key and the core of our work at Bollinger+Grohmann. Structural simulation or structural analysis, environmental simulation, if it's building physics, for example, or facade design. And lastly, we also look at custom developments. So Crumba is one of these, but we also work with many different types of in-house developments to develop tools and workflows for our team. And we, let's say, in Bollinger+Grohmann, we work with 4 main sort of services, and the design technology team works with all of these teams and also in all different phases of a project, because often you might think that computational design is only useful at the start, but as you probably are aware now, and when you go into your construction and fabrication stage, it's very critical on how it feeds into the later design phases too. So from early concept design development through to the construction process as well. So this is like a quick sketch of the first iterations of or ideas of how Crumba first came into play. Back then in 2010, when my colleague Clemens Preisinger and a couple other colleagues finished a research project, they were looking at how to implement the results of the research project into, let's say, a tool. back then Grasshopper still is a very, very popular tool for architects, designers, engineers to sort of experiment with sort of parametric structures or parametric geometry. And so this is why we thought that Karamba would be best fit for Grasshopper, because you have the idea to iterate and optimize, let's say, many different designs. So the traditional way of how engineers would work is that you have a geometry that comes from, let's say, an architect, and this has to be exported into a FE software or converted into a structural model. When you have finished the design, you have to then convert this information back into a geometric model to translate it to the architect, for example. And the idea for Karamba is to couple this all into one platform. And this was Rhino, as I mentioned, where you can have direct geometry input, information about the structural performance, and then feed it back into the geometric model directly. And so, let's see if the video is play. Okay, so I think you already know a lot about Grasshopper and the capabilities of Grasshopper, how you can make parametric structures. Karamba allows you to basically tackle or add this structural information, and genetic algorithm tools such as Octopus, Galapagos, and other optimization procedures can be then coupled with your Karamba scripts. And so there are many different functionalities, not just in terms of analysis and simulation, but there's also form finding. We'll be looking into a bit of that today. Then there's also optimization with cross-sections, the ESO procedure where you try to remove and add elements according to their structural properties. And then also the extraction of results is a very, very key and critical part of reading the information in your Karamba models. And so everything can be graphically displayed, but can also be output as numeric data, because data is often the thing that we're using to, let's say, enhance or sort of build on in our scripts. And then, like I mentioned, how then Karamba can feed into, let's say, your software environment. And this is a big topic that we've been dealing with over the last few years, and it's going to be continuously a big development that everyone's been talking about as well. So how does Karamba feed into, let's say, the work and development at Bollinger+Grohmann? So like I mentioned, some of it talks about the research project, so we're always interested to sort of tackle how the sort of research aspect of Karamba 3D can feed into design, influencing the design as well. These have been, some of these researches then applied into, so let's say, projects. The first one with white noise, the first project where Karamba was fully used to the optimization procedure to design the positions of these random, let's say, randomly angled aluminium profiles. And then the second one for the irregular truss generation of this bridge in Frankfurt. Then going on to topological optimization, where you can start to remove material where it's basically that's structurally needed. So where we then also look at optimizing and rationalizing geometry based on different input parameters. And the last one where, for example, you try to find positions of openings based on the structural logic, and then from this optimization procedure, you start to see that there is a sort of like tree-like branch structure that emerges inherently from the structural logic of the building. And lastly, combining all these elements into intense optimization procedures. This one where we designed the roof, a pavilion structure for a fast charging station in Leipzig, where the column positions were optimized. There are many different, let's say, obstacles that we had to sort of complete, and Grasshopper allows us to try to aim and meet all these objectives. The active energy building in Vaduz, a residential building where basically it's a two-step optimization process to find the optimum column positions. And these columns are also intended as sculptural elements within the apartments themselves, so working closely together with the architects to really design them as elements that are featured inside the building as well. And lastly, as I mentioned, the European Central Bank, where it functions basically like a two-dimensional truss, where these two separate towers are braced together by diagonals. And this was, let's say, one of the very early projects where Clemens used programming to basically talk to RFM, one of our sort of finite element solvers. This was before Karamba, to try and come up with all these different solutions. And then how parametric workflows also feed into later design phases. For example, one key feature is to, let's say, coordinate with existing structures. So point clouds help us to understand any potential clashes or collisions, and these were used for all these three projects to make sure that we coordinate the design of new structures to our existing structures to make sure that we have very little impact or no impact on the existing structures. I'll just go through, but I have a bit more now to talk about the case studies a bit in more depth. A feature project that we worked on a few years ago was this one, a Twist Pavilion. This was done together with a group of students, master students at the Technical University of Graz, the Institute of Architecture and Media. So the client is a sort of a timber institution in Austria, and they approached the university to design, let's say, a group of info pavilions, and these would aim to be scattered around the Alpine region in Austria, and also give some information about the hiking trails, but also about the local timber industry in the region. So the students did, let's say, during the semester, similar to what you guys are doing, different investigations on design, how material could be, let's say, work together, and then they formed groups to then come up with different design iterations. And this group, which designed what they called the Twist Pavilion, was the one that was selected and then built as a first prototype, which stood in the university campus for a year. The students basically came up with a system where thin timber strips or lamellas were basically rotated to form stiffness in the material itself. So we know that when we have a thin sort of strip of timber or even paper, for example, and you put a vertical load on top, it starts to buckle. When we start to rotate it, it adds some additional stiffness. And so the idea was to do this rotation that we could control in a sort of parametric way, so you have a gradient from this rotation, and looking at how this rotation could be used for structural stability. So initial studies in Karamba showed that approximately 30 degrees of rotation gave it much more buckling strength. And they also did then some live one-to-one tests in the timber studio to basically assess this as well. There were 3 typologies then designed for 3 different locations. The typology itself is basically all the same, that you have 2 CNC CLT plates, so cross-laminated timber plates at the top for the roof, and at the bottom for, let's say, the seating elements. These are CNC'd with slots for the timber to, let's say, slide into, and then these are then glued or screwed into position as well. And so there are 3 typologies which are built according to, let's say, the functionality of each of these pavilions, but also according to their snow and wind loads. So the last one, for example, which we call the sort of bus stop typology, this one was critical for where there was really high snow loads and high wind loads, and so we had to actually build in much more, let's say, additional stiffening elements, which are these vertical panels to help stabilize the structure. And so these vertical panels are not only there for, let's say, showing information about the timber industry and also the hiking trails, but also are used as horizontal stability measures as well. So workflow is basically we work very closely with the architects to design the workflow where they have a grasshopper script in Rhino geometry where they could control, for example, the positions of these seating areas and where these lamellas would be positioned, and the angle, of course. this was then fed into a Karamba script where we could give some initial or get some initial feedback on the performance to see if there were critical areas in the design that needed to be first adjusted. And after some iterations, this was then sent into RFM for, let's say, proper validation. The fabrication process, as I mentioned already at the start, is basically you have these slotted holes where these timber elements are slid at the top first, and then twisted and slid into the bottom. This was a system that the students actually developed, and the let's say the fabricator at the end also used a very, very similar sort of method to actually build it as well. And so each of the units were actually totally prefabricated off-site in either single or double or sort of half units, and then brought onto site and basically screwed on the concrete bases. And so here's another one of these typologies where you see the sort of this timber element which sits on top of this concrete base, and the concrete bases were poured on site, so it formed like a seating element for this structure as well. Next project I would like to talk about is a fun project that I got to work on in Sydney. So this is the Rozelle Interchange together with Studio Chris Fox. They're a group of architects, artists based in Sydney, Australia. In, let's say, 20 years ago, the government of Sydney decided that they want to, let's say, design the infrastructure for Sydney and move the highways below ground. And because of this issue, there's a lot of exhaust that comes from the smoke and exhaust from the cars. And so there are specific positions over the tunnels where they need to, let's say, build chimneys for, let's say, releasing this toxic air. And so there are two positions. This is just one of the designs, and there's another one which we also worked on as well, which are used as what we, let's say, chimneys. So they're like 30-meter diameter concrete, let's say, called bunkers in a way. They're approximately 30 to 40 meters tall, and they serve, as I mentioned, to let's say exhaust the air that's from the highway below. And so the vision of the artist was originally to sort of say encapsulate these concrete bunkers with this sort of freeform undulating spiral structure composed of steel, and then there was a sort of system of green walls and facade elements which would then wrap around it. The whole structure is, let's say, sitting on top of like a new urban park, and so that's why they wanted to bring this sort of greenery from the park up into the sculpture and also connect it to the landscape below. Inside, let's say, this sort of steel framework, there are also some stairs, and because at the top or around plus 25, there are some service platforms where the engineers need to go and actually check the quality of the air to make sure that it's actually not toxic for humans as well. And so there are many different components of the design, and so first was trying to work out what these components are, and sort of trying to categorize them so that we can actually come up with a very, very good workflow together with the artist. So here here you can see the sort of different components, the main frame, these bridging elements. To make the project a bit easier, the two bridging elements that you see there are actually the same element, but just rotated 90 degrees. Then there are these rope-like elements which sort of wrap and weave around the towers. The staircases which I mentioned, and then everything is actually pin connected to the concrete tower, because these concrete towers were already built when we built this art sculpture. We could not apply, let's say, too many loads. So one of the main challenges was how to, let's say, build this quite complex structure that would not bring any horizontal loads to this structure, but only, let's say, pin connections, and bring all the loads back into the, let's say, the base or the foundation of the artwork. And then lastly, there's the facade and green wall elements. Here you can see all these elements overlaid on top of each other, And these stitching elements were then one of the key elements to basically hold everything together. And the facade elements, as I mentioned. So what I mentioned is when we work on a project, we try to work out, let's say, workflows that help us to work more efficiently. Let's say in a typical workflow, and it's not to say that we still also don't work like this, but you often get input from an architect, version 1, the engineer or engineers involved go through a whole process of, let's say, importing models to different software environments so that they can do their, say, our daily work. But then a new iteration of design comes, and we have to then redo this whole process. And so the idea is that for this one project, we try to set up what we call a central data hub, where Rhino is the main source of information, or single source of information, where you have the structural information as, let's say, access model, but also the geometric information. It has information about where each component might go in terms of its sort of relationship to each other. This then gets fed into, let's say, the structural model, the BIM model, fabrication model, and let's say a Tekla steel workshop planning model too. And as I mentioned here, basically using different tools, we can extract the data or the geometry from Rhino into all these other software environments so that we can actually have the same information but use other software environments to do the specific let's say, part of the project that is needed for that process. And so here's just an image of, let's say, these parameters that are embedded into all the elements of the Rhino model. So this was then basically the architects developed a master script to embed all this information. So, for example, the information about the structure, but also, for example, when a specific element was last modified. How this element is, let's say, imagined to be prefabricated as of one, let's say, unit, and such. And so we developed mini scripts to basically feed. Let's see if this video works. Oops. Let's see if this video is working. So basically, as I mentioned, using Rhino, we can extract geometry from a structural model, then take the information from the structural model and bring it also into Revit, so that we have also geometry in multiple software environments, but all that have all the same information in them, so that we make sure that the information is not lost during these different work procedures. And then here, for example, one of the complexities of the project was identifying what are different types of connections that are involved. So using, for example, Grasshopper to help us identify it, but then feeding this information into a BIM model so that you can actually then categorize these as different details or typical details. And so here's this documentation of all the, let's say, what we call standard details in the model to sort of, so that the fabricator and assembly on site can basically follow this in detail. Then looking at, for example, this geometric model can be then sent to, let's say, more detailed analysis in other softwares, then detailed into, let's say, for steel workshop planning. So you have all this information embedded there. And here's information. Here's just a quick animation to show all the different software environments that we worked with in the project, basically seamlessly, so that we can extract all the data, as I mentioned. And then in an idealized project workflow, where we have, let's say, input from an architect or, let's say, a designer, we receive the data, and once we get a new iteration, it automatically can update, and someone is informed about this change. One of the key aspects of the project was also optimization and rationalization for fabrication. So checking, for example, the radiuses and lengths of all these elements to make sure that they actually can be prefabricated, but also brought onto site. Using Octopus to optimize these elements according to different parameters. and then comparing them to the original artist's intent and the optimized version. And then looking at, for example, stitching elements, which would be critical to how these weaving elements are basically held together, because basically all these elements are prefabricated offsite, and if there's, let's say, a cut in that element, they would have a different structural performance as well, because they're not welded but bolted together. And these elements themselves were very critical for the global stability of the entire structure, and so we double-checked to make sure their performance, to see if, let's say, these elements could be removed or not. Of course, they were critical to the design from the artists, but we wanted to also validate that they were also important for the global stability. And lastly, I talked a lot about what we call constructability and transport, because often this is something that we don't think of in a lot of our projects, but especially when you're going to be working on your projects where you have to think about the fabrication, is how do you actually get these elements to site. And so this was really one of the, let's say, objectives that we had to control to make sure everything could be fabricated, everything would be structurally, let's say, sound, but also can be lifted and brought onto site, let's say, in a sort of a standard truck size. So then putting all these elements, tagging them into, let's say, what we call trackable parts or components. And as I already mentioned, one of the key critical parts of the project was to assess the impact of this new sculpture on this concrete shell that was already built, making sure that we do not, let's say, overload it with these additional loads from the sculpture, and making sure that the other engineers who designed the other concrete structure would approve it as well. And so then a Tekla model was created from the Rhino model, which was then the basis of the workshop drawings, which you can see here. So every single element was documented in 2D as well for the steel fabricator. Although I did hear that the steel fabricator used the 3D model, the Tekla model, as actually a basis for their fabrication offsite, and it proved to be much easier to understand the geometry than just, of course, the 2D drawings. Which I heard in the other project, which I didn't show today, the fabricators only used the 2D drawings, and they struggled a lot more with building the structure as well. And then also the last thing was also looking at these facade modules, these screen walls, how they come in as, let's say, prefabricated units, and then could be, let's say, clipped onto this sort of steel frame. And here's a sort of rendering of all these elements come into part. So here you can see these platforms. Unfortunately, it's not open to the public, so you can't go up there, but you get amazing views of the city if you do go up there. You can see all the connections that we created, and often this is the case in Australia, where they want to have more tolerance on site. So depending on who you work with on site in the project, who's the contractor or the person assembling everything, was this always ongoing negotiation between how big of a tolerance you give for your elements, because the more tolerance you give, the structure, let's say, the weaker the structure could become. So there was always this sort of dialogue with the fabricators. And this is just an image of the, let's say, this bridging element. So you can see this undulating, sort of woven elements, which then connect this bridge element there. And the last project I just want to talk about today is this Expo Cultural Park greenhouse garden, which opened late last year in Shanghai. This was designed with Delegan Meisel Associated Architects in Vienna. So we won the competition together with the architects back in 2018. The design called for basically a set of greenhouses that would be. Oh, I think I missed the page actually. I'll go back. But the design called for basically a 3 greenhouses, which are set within, let's say, an existing industrial hall. So the site is basically where the World Expo was in 2008, I believe, in Shanghai. There are 4 main buildings, one of them being the entrance building, and then 3 separate greenhouses with different climatic, let's say, regions or zones, and different plants and species that would be housed in them. The architects basically came up with this sort of idea to create this undulating, freeform organic shapes, which would weave in and out of the existing column grid. That's why you have this sort of dynamic shape that or curvature from the geometries themselves, and they sort of envision there's sort of these sort of prism, glass prism blocks, which basically house these green spaces. And so for the structure itself, we looked at one of the main challenges was always how can we maximize the transparency, minimize the structural impact of all the elements. Sorry. So that we could realize, let's say, the intent of the architecture. The forms, let's say, they look quite complex, but we looked at many, from the very, very start, we already looked at trying to optimize and rationalize the geometry. So first, looking at the geometry in plan, the facade, this was one of the very, very first things we did, was to, let's say, rationalize the grid in a way of the facade. So talking with our facade team, who developed also the facade structure, we developed a system where it was a 80 centimeter grid for the facade, composed of either, let's say, straight elements or curved elements or arc elements in a way. So these were then first rationalized using Kangaroo to make sure that we minimize the number of unique elements, so having only straight or pure curve elements, and then pure arc elements. And there was, let's say, a array of 80 centimeter, 160 centimeter, and 240 centimeter facade, let's say, divisions that we would use. The second step was looking at the roof structure. So at the very start of the project, it was envisioned that circle packing or these circular openings was what the architects wanted to use. So we did many, many investigations on how to, let's say, maximize the transparency of the roof. One of the parameters was that there had to be a certain number of operable elements. And so operable elements had a maximum size, I think 3 meters or so in diameter. But of course, the more smaller circles we have, the less transparency we have, because you have more negative space. And so we needed to find a good sort of ratio between the large and smaller openings, because the larger ones would allow us to have more transparency. Oops. So then the facade elements were then converted into this sort of 3D geometry. So these column positions were sort of set up in the script where, as I mentioned, the rule of 80, 160, or 240 facade width were then placed. And then at certain heights, there were these vertical mullions that were inserted randomly in a way. The heights of the heights of the glass panels were preset at, I think, 2, 4, 6, and 8, maximum 8 meter tall elements. And so this allowed us to place these vertical, these mullions, which would also stabilize the columns as well. The structure itself of this one is basically we have this very, very light external facade where we have very slender columns and these very slender mullions. The columns themselves were sometimes up to 20 meters or sort of 17 meters tall, so very, very tall. And so because of this high slenderness ratio, we had to make sure that the elements don't buckle. Global, let's say, stability of the structure is achieved through this courtyard area. So in the courtyard where the architects originally envisioned that they would, let's say, clad it with mirrored elements and could hide structure, we stiffened up and beefed up the column elements and also added, let's say, bracing elements to brace the entire structure. With the roof itself, let's say the negative space or the leftover space from the circle packing algorithm is developed into a sort of like regular grid or Voronoi style grid, where the straight elements are basically encapsulating these circular openings. And then a sort of external frame basically connects the column structure with the roof structure. Although we finally did go with the original intention of a circle packing system, we did also investigate many different strategies for the roof structure. First, seeing the impact on the transparency, as I mentioned, but also on the architecture, as well as also on the structural performance. So one was to take the facade pattern and project it onto the roof. The other one was actually to use the circular profiles themselves as the structure, rather than converting them into straight elements. And the final one was to then connect it to, let's say, cable-like elements below to even reduce the size of the roof beams. And so this was one of the main challenges that we had to achieve, how to minimize the roof design so that we can improve or maximize the transparency. Together with our facade team, we also developed strategies on how the rainwater drainage would be basically designed, and this would occur as a singular package that sits on top of the roof beams, of course. And so this rainwater design is also situated so that it aligns with the roof structure as well. And so, as I mentioned, some of the spans between edge column to edge column is up to 30 meters. 30 meters. And so we didn't want to have, let's say, 2-meter high beams. And of course, this is not the wish from the architect. So how could we achieve it? One aspect which was used in one of the pavilions was to hang the roof beams partially from the existing structure. But in the other ones, we couldn't really hang them because they were not sitting totally under the steel structure. So we developed a sort of hybrid beam cable system where we have the stiff beam from the circle packing algorithm, and we have an independent, let's say, tension and strut, vertical strut system, which ties everything together. And with this system, we are able to reduce, let's say, the beam sizes of the upper beam there. So you can see from initial Karamba studies, we were able to reduce then the, let's say, the height to 1.62 structural height for a span of 30 meters, which included, for example, these vertical struts and cable systems there. And then trying to evaluate if we use a bidirectional or tridirectional system. I think in the end, the bidirectional system, sort of a quasi-bidirectional system, was adapted where we had super large spans, and where we didn't have larger spans, they were not placed anymore. And so all of these studies and all of different iterations were calculated in Karamba 3D first. So first checking, of course, the utilization of the roof structure, making sure that where there are critical elements of our roof, and then also looking at displacement. So of course, where we have the largest spans, where we have displacements, but making sure that the displacement of the roof structure meets the facade demands or requirements as well. As I mentioned, we also were working on the facade structure, and through the rationalization process at the very start, we were also able to minimize the number of curved glass elements that were needed. And so in the end, there's 6 different radiuses or radii that were used, and then of course we have the straight elements as well. As I mentioned, the facade structure was very, very critical because of the slenderness of all the columns. What was very, very critical was understanding the buckling and how the structure or how these columns would buckle. we will be going a bit through buckling today in the workshop, but basically what we were able to do was actually reduce the buckling length of many of our column structures by taking into account, let's say, additional support elements of the interior, actually. So in the greenhouses themselves, they often have, let's say, multi-story landscaping elements, which were designed as concrete. And that's why we have on the right, you can see that some of these supports in the middle or like towards the bottom of the column, and these are situated where we can essentially tie the columns back to these concrete elements and in a way reduce the buckling length of these columns. And so, as I already talked about, minimizing the, let's say, the impact or the structural elements was critical. We had to really detail all the different components together with the facade team to really understand what is the maximum or minimum roof package that we needed to be able to design it so that it could be filled, basically meet the architect's requirements. And then here's some images from the construction site. So here you can see all the three main structures that, so there's the longer one at the back, and then there's the two ones, and then the one that I showed in detail is the one right at the front. Here's an entrance building which is similar in geometry but has a totally different structural system. That one is more of a sort of steel column grid, or let's say with a sort of regular, let's say, steel grid beam, where we could support the, let's say, interior as well. Here's an image then of the entire structure with all the different facade elements already completed. And so here you can see the circle, oops. So here you can see all the circular roofs of all the elements. The facade is quite transparent and so it fulfilled basically the architect's intention. I'm just going to skip through a few of these photos from the construction site. So here you can see all the facade elements coming together. We have this edge beam that encapsulates the sort of connection between the roof and the facade. Here is the one greenhouse that doesn't have any of these tensile elements inside. So this one is partially hung from the steel hull above. And of course, what made it even more complex are these what we call auxiliary elements, which are embedded inside the greenhouses. So of course there's like free floating ramps and other staircases which the visitors need to use, so you can visit not at just the ground floor but also at different heights, and these had to also be, let's say, suspended from this our roof structure. So that's why you have all these complex cable systems then tying it back to the roof and the facade. Here's one where you can see this sort of grid of tensile elements that I was mentioning, that they then connect back to the edge of the beam, or edge of the facade. And in this image, so as I mentioned, the original architect's intention was to clad the courtyards, but in the end they kept them all open so you can actually see this mega, let's say, stiffening elements in the void area. And so just a couple more images from the just before the opening. And so I think with this project we were able to achieve the architect's vision of having a very, very transparent and very light so structure that really embeds together with the nature. And I just want to end with sort of, let's say, an outlook of what I've talked a lot about like developments and workflows, but of course we are continuously trying to, let's say, improve the way we work. And we all know that, for example, let's say 50 years ago, or even still today, we're often working with paper files. Now we have a lot of files, but they're all just digital, right? So this mess has just been, let's say, brought into the computer on servers. And the problem is still that all data is fragmented, is disconnected, and it's still a very manual process. And so one of the big challenges that many people are now sort of looking at is how can we, let's say, use all this, or how can we connect all this data so that we can actually access it and really work with it. And so we're trying to find out ways to leverage on this knowledge and data that we all have in our company. And so, for example, one of these is looking at ways of working. Design flow is a sort of a project, in-house project that we're developing to help, let's say, engineers who are, let's say, not BIM savvy, let's say, have an impact on how, let's say, BIM models are created. So there's like a sort of, by leveraging on Speckle, which is a sort of a cloud AEC platform where you can upload your 3D models and sort of interact with it and comment on it. But now we are creating tools that allow engineers or like other designers to, let's say, add information to an existing model that they don't have to go into Revit and actually add it, or do it, for example, in a PDF markup, which is the common, or let's say a print markup, which is still, let's say, very common. So this information is then fed directly to the drafter, who can then input it or basically put it into their 3D model as well. Of course, with the environment, looking at the carbon footprint, how can we, let's say, gather information on the impact of our structures? So trying to assess, let's say, the carbon footprint, the embodied carbon footprint of all of our structures, to have an understanding of what the buildings that we design and how their impact is on the environment, and how can we then benchmark this and try to improve for the future. So developing workflows that allow, let's say, geometry to come from multiple platforms such as RFM, Cramba, IFC, or even like a standard Excel table that can then be fed into like a database to then have an understanding of this information. And then, like I mentioned, how can we connect all these tools together so that we no longer have to have, let's say, a middle person really translating this data from one software to the other software. I've talked about that in, let's say, this sculpture project in Sydney a bit, but trying to leverage this into, let's say, a more standardized process as well. And using data to help inform the way that we work and understand, for example, the impact of our structures. And so here, this data that comes from the, let's say, embodied carbon analysis could be fed into what we call now dashboards. So Power BI allows us to then interact with these models, find out, you can do different sort of what we call like mapping, compare, for example, different models to understand, let's say, how one project can relate to another project, and then you can start to understand if it's performing better or worse based on many, many different objectives or data inputs. Yep, and thank you for listening. I mean, this is, I mean, you always have to then sit down and really work out what are the things that you want to optimize, because if you try to optimize everything, then you're never going to optimize anything. So I think that's why we set up the optimization procedure for really specific parts of the project. So like I said, one step was to first optimize, let's say, in a way it was more rationalizing, not really optimizing, but more rationalizing the curvature of these rope, what we call rope elements first, that allowed us to then, let's have a first iteration of, let's say, having a rational or more rational geometry as compared to the original input geometry. And then the second part was into, that was more optimization, was finding the best positions of, let's say, diagonal elements to stitch these rope or freeform curve elements together. One, so that they can be structurally, let's say, sound. So one of these parameters was making sure that every rope was at least connected, so that they're not flying, of course. so that they were interconnected with each other, but they were also connected back to the main structure. So there were two sort of, let's say, key drivers of how the optimization process worked. So I think if you start to say that everything's up for optimization, it gets very, very complex. And I think now, what we've found is that a lot of the projects we work on nowadays are not really optimizing, let's say, global geometries, but really focusing on a specific aspect of the project to optimize rather than letting the computer solve everything for us, right?
For the tunnel chimneys project, were all the steel elements required structurally? Or?
So this was a funny story because when we designed the project, we designed everything as steel because steel has a much higher performance than aluminium. But when the project was then taken over by the Chinese partners, the roof was redesigned as aluminium because it was an aluminium manufacturer who actually got the project. So of course they wanted to use aluminium, and they in a way reinterpreted the design in a way that not only the sort of frames that I showed before where we have this Voronoi system were the main structure, they actually had to, let's say, use the plates of the cladding as well as the, let's say, the circular rings for the openings to actually utilize the entire structure. So that was very, very critical in sort of, let's say, the design process from when we sort of stopped our part and then when the local partners took over. But of course, when we talk about optimization and what we call structural optimization and structural design, it's very important that you optimize stuff that's performing very high, but you also should make sure that your stuff, that the elements that you design are not performing very low, because then it's also not optimized. So we always make sure that we check that at least most of the elements are not below 50% utilization, because then you're basically building elements which are obsolete, right? So we also try to minimize, let's say, elements which are what we call not needed for the structure. And this might mean that, for example, we see further opportunities to optimize because we can maybe reduce, let's say, the wall thickness of a steel element, right? If it's underutilized. Because a column that is only 20% underutilized is basically a waste of resources as well. So it's not just optimizing for the top limit, but also making sure that your elements are not underutilized as well. And that's also a very, very critical thing that often you don't think about, but it's also very, very important to assess.
Just a minor question, but do you have experience in the group using Karamba as a teaching vehicle of structures in university?
I mean, so Karamba was, let's say, when Karamba was first, let's say, brought out into the industry, it was very much very academic because as a tool, universities, and especially more architecture students, really jumped onto this our excitement of Karamba. So it has this whole history of being embedded in academia, and I think that's where it's very useful because you can actually change something in the parameters and see live what that impact has on your structure, right? Exactly. So as a teaching tool, it is very, very beneficial. I think one of the disadvantages that maybe Karamba has brought is that people who don't have an understanding of structures put their structure into Karamba. They might have actually modeled it incorrectly. Karamba might show, let's say, a result that shows that it's working, and then you might just assume that your structure is already working, right? But it's not, let's say, such a linear process. And so let's say this is the challenge of really getting to Karamba and using it really into your projects, that it's not just about, let's say, getting a utilization below 100%, but it's also actually checking to make sure that your structure is actually performing as you intended it to. And if it's not performing as you intended it to, understanding why it might be, let's say, wrong. And this often might be, let's say, a definition in terms of how you set up the connections, for example, or buckling length is a very, very common issue that can make your structures perform much better than they actually do in real life. And so there are many great advantages of using Karamba in teaching, and I think we can see that already, I think, with a lot of the students and teachers who use it in academia. But I think, like as I mentioned, there's always this sort of drawback that there is a misunderstanding of what Karamba can do too.
Okay, thank you very much.
Hello, I'm curious about at which stage in the design process you usually start structural optimization, because what personally I do, we think first of the geometry, the architectural geometry. We try to get that solidified first, and then we start investigating structurally. So I'm curious about your process. When do you start doing that?
So typically, I mean, it depends on project to project, and let's say how collaborative we are with, let's say, the architects. Often it might be that an artist or an architect has already come up with, let's say, their vision of what they want, and they're very strict with what they want to achieve, right? So there's, let's say, little room to what we call optimize or play with the geometry. And oftentimes then the architect is very, very open to optimizing, let's say, everything, right? They, let's say, have a box, and then you can put anything inside the box, right? So there are many different types of projects, and we see the best potential is when we do it at the design concept stages. So really designing structures together with the architect so that the structures really push the architecture even further, right? That the structure is not an afterthought that you just have to apply to make your architecture intent work, right? So I think this is where we see it, the projects being much more powerful when the structure and the architecture really read as very, very coherently as, let's say, one language, that there's no overpowering of the structure over the architecture, but vice versa, right? Different architects have different visions of what they want to achieve, right? And so this is always this let's say, experiment that we have, right, on how to fill the vision of the architects, but also trying to make sure that the structures that we design are efficient, cost-effective, and fulfill all these requirements, right? So it's hard to say when there's an exact stage, but I think the earlier we come in with, let's say, optimization or, let's say, design input, I think the stronger the project can be. Yeah.
Thank you.
Okay, thank you very much. I think we can call it a day.
Yeah. And maybe just to add to that, I think when you're, let's say, it's not really a purely optimization stuff, but this relates more to embodied carbon, LCA. So there are many studies done that if you do, let's say, carbon or optimization for carbon footprint at the very early stage of the project, you can have much more impact than if you were to look at it only at the, let's say, end in the tender process, right? Because there's little opportunity for change, right? So you cannot change much then. So I think the earlier you start looking at stuff, it's not also structure, but also other impacts or other fields that can be performing much better at the end result. Yeah.
Okay. Then
Thank you.
Thank you. Let's have a half-hour break.